Hello, in this video we're going to talk about graphs. Okay, so a graph is a data structure that consists of a set of nodes and a set of edges that relate the nodes to one another. A vertex is a node in the graph. An edge, or an arc, is a pair of vertices representing a connection between two nodes in a graph. An undirected graph is a graph in which the edges have no direction. A directed graph, digraph, is a graph in which each edge is directed from one vertex to the other. There's also the notion of weighted graphs, and a weighted graph is where each edge has a value. Okay. So let's consider the formal definition. A graph G equals a tuple of VE, where V of G is a finite non-empty set of vertices, and E of G is a set of edges, written as pairs of vertices. So here we got V of G, the vertices A, B, C, D. And here if we got the edges, anywhere there's a line between the two of them, we've got A to B, A to D, B to C, A to D, and B to D. Given G1 is undirected, the order of the vertices doesn't matter. That is, edge from G1 equals, at the edges of G1 equals BA, DA, CB, and DB. For a directive graph, A to B matters, is written as A comma B and means from A to B. So A to B is not the same as B to A. A and B are adjacent, and A in this case, and A and C are not. For directed graphs, A is adjacent to B, and B is adjacent to A. For non-directed graph. For a directed graph, B is not adjacent to A. A directed graph is a graph where each edge is directed from one vertex to another. So here's an example. Notice here, we've got these different nodes. We've got 11 is weighted. 11 has an edge from 11 to 1. 1 and 3 have edges to each other. You cannot get from 11 to 9. And 9 has an edge to itself. It's called a cycle. A tree, as we discussed before, is a special case of a directed graph with the root adjacent to no one, and each vertex is only adjacent from one to one other node. A path is a sequence of vertices that connect two nodes in a graph. This graph has multiple paths. If we wanted to get to C, we could get it to from A. We could get it to from A, B, C, D, or D, C. A complete graph is a graph in which each vertex is directly connected to every other vertex. It's a direct path. Okay, so in a weighted graph, each edge carries a value. So say there's an airplane flight. It'd be from San Diego to Seattle is 75. From San Diego to Austin is 100. Austin to Atlanta is 100. And Atlanta to Washington is 10. So, in theory, if we wanted to go from San Diego to Chicago, the cost if we went through Seattle would be 75, 150, and then 35, 185. But if we wanted to go through Austin, it'd be 100, 180, and 215. So it's cheaper to go through Seattle. So, now, there are different types of traversals we can talk about. In a layered traversal, we do what's called a breadth-first search. Whereas when we go layer by layer, we got A, then BC, then E, that should be F, G. So, that is a breadth-first search. How do we do it? Starting at A, we look at its attached children. We've got B, C, and E. From there, we go from F to G to H to J, and finally, we'd go from the total thing would be A, B, C, D, E, F, G, H, J, I, D, which I don't know why that's out of order. But anyway, this is made use of a table for keeping track of things. Now, when you implement this, we begin to start combining our various data structures. So, for example, breadth first search. Let's have a Q. We're going to label a root as discovered, given a node. We're going to enqueue the root. While Q is not empty, grab that first item, the vertice. If it's the goal, then return V. Okay? In other words, if we're at the edge, the final. For all edges from V to W in G.adjacent edges, if W is not labeled as discovered, then label as discovered and add it to the queue. So basically what this will use is it use a queue to control us going layer by layer. Okay? For a depth first search algorithm, each vertex... Okay, so now we're going to go on. First we'll take a look and then we'll go on to the depth first. So using this data structure visualizer, we'll see that even though you can use breadth first search on a binary tree, for a generalized graph, you have to give it a starting point. So let's say this guy starts at 3 and we want to go breadth first. Remember, it's based on actual connections. So starting bracket, and we will start running it. It will mark 3. Notice it has an array that it marks. And then it's going to go and queue all the various items. Here's the queue it's actually showing. Okay. And it will walk you through the entire thing. Now, I want to slow that down a bit so we can take another look. All right, here we go. Let's start this time. Let's start at 0 this time. Okay. So here we're going to mark 0 and get its children and put them in the queue. Right. Then we're going to go to the children and go through them in the queue, and we're starting at 1. Okay. Notice that even though a node shows up in twice, it's not going to get repeated because it's not on the same level. Okay. And we're slowly going to walk through each node, marking them as visited. And once all the nodes are visited, we're done. And it makes sure to visit every node in a connected graph. Going back to make sure, pulling from the queue until the queue is empty. And finally, all the nodes have been visited except the start node, because we already visited, because that's where we started. Okay, so now we're going to look at depth first search. For depth first search, each vertex is visited, then each unvisited vertex adjacent to V is visited. If vertex V has no adjacent vertices, or all its adjacent vertices have been visited, backtrack to the predecessor of V where the traversal started. If there are still some unvisited vertices in the graph, the traversal continues, restarting from one of the unvisited vertices. So here's an example. It kind of looks like, for a tree, it looks like a preorder traversal. A, and then B, D, E. So basically, it's going as deep as it can get in the graph. All right, so starting at A, we're going to use a stack this time. A, B, D, we're going to pop back to B, F. So then we see that E also has a path back to A. So looking for a path to a vertex that has not been visited. Okay. So then we come back and get back to A. So we go to C. C gets to G, and we're finished. This is why we need to keep a list of vertices that have been visited so we don't visit something twice. So here is the algorithm. And instead of actually using a stack, we can use a recursive algorithm. So for each G, V, label V as discovered for all directed edges from V to W that are in G dot adjacent edges. If the vertex is not labeled as discovered, then call it on that new vertex. So let's take a look at the depth first search now. Where is it? Okay, ready? So now we're going to take that same matrix or a graph. Let's say we'll start at 6. Start at 6, and this time we go deep. You see, we're going deep this time. Notice that there's no way out of this one, so you got to go back. And we're going to come up here. Notice that 6 ends pretty quickly because it's a directed graph. Let's change it to an undirected graph and try that again. This time we'll start at 0. We'll start at 1. Okay, so we start at 1. We go to all its children. We walk down as far as we can. Okay, notice we're just using the arrows to show where we're going and what we visited. So I'm going to come back here now. I'm going to go to where else we can. Okay. Now, we don't have to go back to 2 because we know it's been visited. Okay. And we can continue going through, making sure we don't have to revisit where we've already visited. Pretty clean little algorithm. Okay. So now here comes the question. How do we actually build a graph? This will be one of your homework assignments. 2 major ways. A 2-dimensional array, a matrix to represent a graph, U to V, and it's true for edge and false F if no edge. So from 1 to 2, there's an edge. From 1 to 2, there's an edge. Okay. But from 2 to 1, there's not an edge. Okay. From 4 to 3, there's an edge. But from 3 to 4, there's not. Pretty simple implementation. It does have a couple downsides. We'll come back to those. You can also represent a weighted graph this way, where instead of having true or false, you'd simply have the weight or some special symbol representing infinity, meaning no way to get there. So if there's no edge, we say infinity, but now we know the weights. Okay. There's another option, is we could do what's called an adjacency list. An adjacency list is where we have a vertex, and we will have each edge, we will have a representation from each vertex of the node it can reach. So from here, we've got an adjacency list 2, 3, and 4 from 1, because we can get to 2, 3, and 4. From 2, we can get to 4 and 5. From 3, we can get to 6. Okay? In an undirected graph, the edges may appear in 2 lists. Now, the advantages, you can also do the same thing with weights, but you still now have to record both because you need to know the edge and the weight to it. Now, the advantage to using a adjacency list versus an adjacency matrix is space. The advantage to an adjacency matrix is speed. But if you have a lot of unused entities, you can waste quite a bit of space with an adjacency matrix. After this, we're going to go into algorithms that use these things.